Hello, and welcome back to Stat 3050 at the University of Wyoming. We're online, but boy, we're just having just a grand time. We really are. And today, we're going to be doing an example on how regression can be used for prediction. And so just like last time, I've got some goals that I want to get through, just 3 this time. I want to meaningfully subset some data, the data that we're going to be working with. And then I want to introduce log transformations and exponentiation. And then I want to use some regression model to predict some unobserved data point that we have not seen yet. And like always, this example is brought to you by ex-members of Genesis. More specifically, these ex-members of Genesis, Phil Collins and Peter Gabriel, specifically these albums from these ex-members of Genesis. No jacket required, and so just hitting it the whole time. Just so good. Just so good. All right, so let's go ahead and get R pulled up and ready to go. Okay, so we've got R opened up, and I also want to show you just sort of what's going on with these data. It's actually very interesting, and I want to make sure that we're sort of on the same page as to what exactly is going on. So we're going to be working with this fire abundance data set. And so you can read the kind of description here. Pretty simple, but what's really going on is we have 2 columns. One column is based on going into some woods and is essentially just looking and counting at the number of fire scars in proportion to places that do not have fire scars or trees that don't have fire scars, essentially is what's happening. So these are all proportions. And then we have this other column doing the same thing, except this is like a cheaper way of doing it. So instead of hiring a bunch of people and going into the woods, they hire like a pilot and they just look down and sort of estimate it by that. 2 totally legitimate ways of doing it, but this one is sort of known for being more over-under than the search-based method. And the search-based method is more or less sort of the gold standard here, but very expensive, right? So what we want to do, we want to use this column as our predictor, and then try to predict what this would be, the search-based method, predict what that would be based on our probabilistic method. All right, so these data are already collected. They're very long, counts of I think about 250 or so, 249. So this data has already been collected, and we're just going to try to almost make a new model based on these 2, right? Okay, so we've got that cleared away. And then, so we'll open up R. Looks good. And I'm going to do the same thing I always do. I'm going to come up here to Session, Set Working Directory, and choose Directory. I've got my data. I know that I've got my data stored in Simple up here, Simple Regression. So I'm just going to open that. So, and then I don't have to do that every time. I can just copy and paste it. So set WD, just do that. We run that again, nothing will happen, but if we run it again after we close R, then it will set it pretty quickly there, so it's all good. And then we'll just read in the data. And that data is called, I'm going to call it fire here, just so we know. You could call it whatever you want. And then I'm just going to say read.csv, quotation marks, and I have it called fire.csv. So I do that, and here we are, bingo, right? Take a look at the data, and we've got the same data that we saw in the Excel spreadsheet. So we have 3 columns. We have one column for the site, sort of the location of the measure, and then the search-based proportion of fire scars, and then the probabilistic method of measuring fire scars. Here, so this is all sort of paired. This is the same plot of land here, and we see that there's a few of these are pretty different. This one, the second observation here, is pretty similar. So we're going to try to model this in an attempt to keep doing this probabilistic method, but sort of correct for any deficiencies. Okay, so what do we want to do? Well, first I want to rename some of the data, using this names function here. And then I'm just going to say, because I don't want to have to type out probabilistic all the time, because good lord. So I'm just going to do LOC for location. I'm going to do search for the second method, the search-based method. And then I'm going to do prob for the third method. Okay. Now let me sort of make some more room here too. Great. And then I want to plot the data. Plot the data. Here we go. So I'm going to use the library tidyverse. It's got the ggplot in it. And I could easily come up here, and I already know, actually, I already know what libraries I'm going to use. So I'm just going to do this. Very cool. Tyberry library. And then I'm going to do, I also know that I'm going to need the ggfortify, right, for the residuals. So we'll run that too. And then we're all set. So then we'll use the ggplot function. And then the data is going to be fire. And the aesthetic is going to be x equals, and then we're trying to predict the search-based method based on the probabilistic method. So what we're going to do, we're going to make our x, our predictor, prob, right? That's our predictor. And then y is going to be search. That's what we're trying to predict, right? And then I'll just clean up these parentheses just a little bit. No big deal, no big deal. That only aesthetically changes the code, not functionally. So if we run that, we'll get a blank slate here of sort of the range of data that we have. And then what we want to do, geom point, nothing in there, and then geom smooth, where the method equals lm, and then we can clean up the background with theme classic. Right, just sort of running one line at a time to make sure that it's doing exactly what we want. And it is, which is great. So what do we see? So we'll come over here to the plot, and we see some interesting behavior. We sort of see, we have a lot of zero values for both, right? So here, when this sort of vertical line here, that's when the probabilistic method said that it is somewhere close to 0. And actually, let me zoom in here so we can see it a little bit better. So when the probabilistic method said it was estimating, 0, it was estimating 0 burns there, it actually turned out that it was, not. It was some non-zero proportion of burns. And then the same thing here, too. When the probabilistic method said, hey, there's actually some burn here, it turns out that there was not any. So this is sort of more or less, this is the truth, and this is more of an estimate, okay? So we're going to try to correct for that. And in fact, we can actually just get rid of these values, because maybe the purpose is not to estimate where there is none, but maybe we do just want to see sort of what the history is when there is a burn there, the history of these burn scars. So we'll get rid of that. But first, let's actually just make a model. I'm going to call this model with zeros, just so we can keep track of everything that's going on. And what we're going to do, we're going to say this is model 1, because I know I'm going to make a few more. I'm going to make a model 1, and it's going to be lm, and then I'm going to use this formula argument, and it's going to get search as a function of prob, and the data equals fire. And then we just hit it with this summary.lm, model 1, run that, and let me zoom this in just a little bit, zooming in. All right, what do we get? Well, we get the call, and everything here looks good, right? Search as a function of prob. And then the residuals, we see the min and a max of the residuals, and we see that it's centered right around 0. More or less symmetric around here. A little less symmetric as you get further away, based on the min and the max. That's fine. That's okay for now. And what do we see? Well, shoot. We get an estimate for the intercept, and we get an estimate for the slope, but we don't get an estimate for, we don't have a significant p-value. The p-value is greater than 0.05. The slope is fine. The slope says, okay, as x increases, y increases by 0.9, in some sense, right? But our purpose is for prediction. We need both of these. We need both of these estimates to be statistically significant, which we do not get. So do I even care? Well, let's see what the issue is. So what I'm going to do, I'm going to auto-plot the residuals. I'm going to auto-plot the residuals. I'm going to get rid of the smooth color, and I'm going to clean up the background just a little bit, just so I can see. And what do we get? And we're going to have to zoom this in too, because it's going to be kind of funky. I can already tell. Yeah, here it is. Okay. Well, so what do we see? Well, we see these, we saw that in the regular plot, in the normal plot. We sort of see the geometry here of these 0 values based on values that actually were not 0. The same thing here. So this is a clustering, that we need to kind of figure out. This is not good for us. But let's just kind of get rid of that in our own mind. And what else do we see? Well, we sort of see that it's fanning outward. And one thing about residuals and looking at it, visually, takes a little while for the eye to get experienced at catching these sort of things. Because this is sort of influencing your eye to see maybe more fanning than there is, or maybe even not enough fanning. But we can kind of see here that the clusters are right around here, and it fans out, and it's not scattered equally as you get further away. It kind of gets a little bit less, it kind of gets a little more sparse as the residuals increase. Okay, so I'm not even going to worry about the histogram now, because this did not meet my second assumption, equal scatter. Okay, so that's not good. So what do we do? Well, what do we do? Well, just another great question. Just an absolutely great question. So what we're going to do, let's first try removing the zeros. Let's remove those zeros and just see. Maybe the plot, remove zeros. Maybe the purpose of this study is just to see, when there is a fire burn, or a fire scar, rather, when there is something, how good can we predict at that? How good? So maybe they have some system where they're only looking at places that are for sure burned. So that's okay. That's good. So let's do that. Well, so how do we do that? Let's make a new data set. We'll call it Fire 2. And then we'll use the data from Fire 1, from the original data set, Fire, not Fire 1. And then we'll use this pipe operator, this percent greater than percent, and we'll filter out, and then we'll filter out the values greater than 0, right? We only want the values greater than 0. So how do we do that? Well, we just we'll put in our first column, search. We want that to be greater than 0. And then we also want prob to be greater than 0. We want that to be greater than 0. And we use the ampersand sign here, this and sign, just to say do both of these, not just either or. Okay? So if we run that, we can click on this and we see that the observation count has decreased. Still pretty large, so that's good. That's good. And then we see that there's, by eyeballing it, there's kind of no more zeros left. So that's all right. That is okay. So then we can make a new model. We'll call this Model 2. And then let me actually make a little comment here that we're modeling with no zeros. Okay, so Model 2 is going to get linear model, and then we're going to just put in formula, same stuff, right? Same stuff. Search as a function of prob. And then the data is going to be not from Fire 1, or not from Fire, but from Fire 2, the one without the zeros. And then we'll just hit it again with the summary.lm, put in Model 2, run that, and let's see. Hey, we see that the residuals still sort of look the same. That's fine, just based on this. But look, we now get significant p-values for both of our estimates, for both the intercept and the slope coefficient. So that's pretty good, right? That makes it a lot better. So we're done. Not actually. The last thing we need to check are the residuals, right? So we'll do this. Now we'll do autoplot equals, autoplot, and then the object is our model. And again, just getting rid of the smooth line that it makes a little bit misleading sometimes. And we'll clean up the background too. Great. And let's zoom in, and see what we can see. Uh-oh. Well, what do we see? Sort of the same situation. In fact, I think we can even see it a little bit better now. We sort of see this fanning outward, as as the residuals, as a fitted value increases, the residual sort of goes all over the place, right? So this sort of clustering over here and sort of fanned out, very sort of sparse data points over this way, sparse residual values over here. So that's an issue. That is not good for us. So what do we do? Well, recall that one of the goals of this example is to show you what a log transform can do. What a log transform can do. So what is a log transform? Well, essentially what it does is that it just rescales the data, and it treats, the log treats smaller values differently than larger values, and that's why we use it. That is why we use it. So we're rescaling the data. We are not manipulating the data. We're not, breaking any rules by doing this. But we are going to maybe help our case out just a little bit. And so again, with the data with no zero, I think modeling only has one L. I think I did it up here too. We'll just fix that because we're all fluent in English. Okay, at least you're more fluent than I am. Okay, there we go. Okay, so we're going to be modeling, still again, with the data with no zeros. Modeling data with no zeros, right? Just for now, just for the purpose of the example. And so how do we log transform? Just another great question. It's pretty easy. We could do two things. We could come in here into our data and we could mutate. We could use that mutate function to make two new columns. One of the log of the search and one of the log of the probability. If we wanted to look at the summary statistics of that, we could. But it's not really too important to do it, to make two new columns, right? So what instead we can do, we can just say model 3, and it'll get the same stuff. It'll be formula, equals, and then it'll be search as a function of prob. And then data, the data comes from fire too. Okay, so right now this looks no different than what we've done before. Let me make some room here. It looks no different than what we've done before. Well, that's okay. What we can do is we can just type in log here, and we can take the log of this variable, and that's all it's going to do, the log of this variable. And just a quick note, in R, log this, log that, is the natural log. So that's cool. Just good information to know. And then this space, just ignore this space here. If we run that, we've now log transformed our y variable and kept our x variable the same. And so I'll show you again in a future PowerPoint how exactly to know when to log transform and what it does. So I'll show you in the future, in a future PowerPoint, what to kind of look for that is indicative of needing a log transformation. But for right now, I'm just going to kind of guess and just see what happens when we log transform y, just to see. So I'm going to hit this model again with the the summary.lm and our model 3, and let's take a look. All right. So now our coefficients for the intercept and the probability, the slope probability, are both very, very low now. We are very certain that these estimates here can be trusted. Very certain. We come down here and we can look at the r² too. We get the spooky number, right? Don't pay too much attention to that. And we see that the difference between r² and the adjusted r² is not that much because we have a pretty big sample size. So then, this is all good, but let's look at the auto plot. Let's look at the residuals. So, same thing, same story, right? Getting rid of the smooth color, getting rid of that smooth line, I should say. And then cleaning up the background. We do that. And what happens? Well, booyah. Look at this. things have spread out a little bit more. We see more equal scatter. It's still sort of sparse out here, but that just might be a characteristic of the data, you know? It might be highly improbable that there's a lot of fire scars in certain areas, right? Maybe it makes more, you know, ecological sense here that, you know, you only have a small sort of proportion of fire scars. So that's all right. So now we see that, hey, our residuals, our assumptions are met based on the residual plots. There's a goodness of fit. The scatter is fairly equal, and, you know, right now we can take a look at the histogram of the distribution, but for right now, like, most of these points are on the plot, they are on the line. So we will take just a quick look at the residuals, and we'll see here that slightly left skewed, only slightly though, nothing too crazy. No major outliers in the residuals. So if we were to draw a curve, it would only be a little bit skewed, and so that's fine. The other two assumptions are met, and this one is decent. This one is okay. Well, so what does our regression equation look like? Well, I'll show you. So, just sort of typing it out here, it's not going to functionally do anything. We've log transformed y. We have log transformed y, remember. Okay, so what that means is that our regression equation just looks like this now. Log of y equals, and then let me quickly look at our intercept. Okay, so I'm going to do some rounding here. No big deal. Negative 2.43 plus 2.96x, or something like that, right? So if we wanted to, in the future, we would just plug in x and then do the quick math here, and then we would get some estimate. However, we would get the log of that estimate. Well, so what do we do? What do we do in that case? So that's our regression equation. Let's do some prediction. Let's use that predict. Let's use that predict.lm. Okay, and our object is going to be model 3. Our object is going to be model 3. And then our new data, we're going to put it in a data frame. And then the prob, that's going to equal something. And so let me take a quick look at our fitted line plot there. Okay, so where do I not have data? Where do I not have data? Well, sort of over here is a little bit of a blank spot, maybe this sort of gap right here. So I'm just going to, for fun, put in 0.6. For fun, just to guess, right? Well, what does that get us? Okay, cool. So that gets us a negative 0.649. We're done, right? That makes sense. Well, no, it doesn't. Of course it doesn't. You can't have a negative proportion of something, right? Okay, so what we do to undo this, if we have logged y, so to undo a log transformation, all we need to do is exponentiate. And we use this exp function to do that. And I can just copy and paste this value in there, run that, and then we see here that we get something that makes a little bit more sense. It's put back on the normal scale, right? So that's what it equals, about 0.52, right? 0.52. And so that's really all you need to do. If you have a log transformed y, all you need to do is just exponentiate whatever value you get back, and then you'll see that it gets put back into this original scale units. Pretty cool, pretty simple, right? It does take some practice and does take some getting used to, but this is pretty much it. So just a quick note. Log, to go back, we'll say exponentiate, and then original scale, we'll say. Okay, so you're originally given some log y, we'll do it like that. Exponentiate, you exponentiate log y, and that undoes it, and that puts it back in the original scale y. Very cool. And just another thing too, if we come down here, we can get very efficient. We can get very efficient with our code and say exponentiate, and then if we just copy and paste our code in there, we'll see that it gets us the same thing, right? So it automatically puts it on the original scale. Pretty great. Pretty great. Now, just a few notes. These data, they're a little funky, and so using a log scale might not be the best way of doing it. But for this example, it's a really good example of showing how log transformations change the scale and make your assumptions met. Again, we're not manipulating data in any kind of way. We're doing legitimate transformations, nothing that's breaking any rules. Just to note, interpretations for log transformed variables can be super tough, and they can get complicated very quickly. So we're not too much going to worry about it in this class, as most of the time in research and in papers and stuff, you don't really ever see that sort of interpretive sentence for regression in general, but just sort of knowing that it can be very complicated sort of makes everyone feel better about not reporting it. So that's why I've shown you how to do this. Predicting a new value for y, and then just exponentiating it back sort of makes things a little more easier to understand. Okay, so I believe that's all I have to say right now. Of course, we will do more examples here in the future. And if you have any questions, just let me know, and I will see ya next time.